Number 4. So what equation explains the relationship between restoring force and the displacement of a spring? This was in part A of the lab, so you've already seen this equation before. It's this, Fs equals negative Kx. Fs is the force of the spring. K is spring constant. X is displacement. And that's always from equilibrium. There you go. Simple enough. So the force is dependent on the strength of the spring and how far you are from equilibrium. So what's with the negative sign? We've talked about this before also, but it's worth reiterating, and that is that Fs and X are always, that is not how you spell always, in opposite directions. Always, 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 always. So be really careful on problems. Either F or X has to be negative every time you solve this. So if I lift something up, that's a positive X, which means F is negative. Okay? If I pull something down, that's a negative X, which means F is positive. One of them has to be negative every single time. Either F or X has to be negative every time you solve this problem. Okay, so let's do an example. So what is the spring constant for a spring that stretches 25 centimeters when a mass of 0.2 kilograms is hung from the end? So we have a spring that looks like this normally, and so here's what I would call 0. And then we put a weight on the end, and it stretches 25 centimeters to some new equilibrium. And that value here is going to be 25 centimeters. There. So, what is the spring constant? So we're solving for K. It stretches 25 centimeters, so that's X. Now it needs to be in meters, that's why it's bold. So that's 0.25. So I divide by 100 to go from centimeters to meters. And the mass is 0.2 kilograms hung from the end. Okay, so when I'm setting this up, I'm setting up the equation F equals negative Kx. So F is not here, so I'm just going to leave it blank for now. Negative K, I'm solving for K, and X is equal to 0.25. Since I'm stretching it down, I'm going to call it negative 0.25. But that doesn't change the fact that I don't know what F is. So this is where I have to think about what's going on. I say to myself, okay, what's happening? I'm putting mass on the end and it's stretching it out. Why is it stretching it out? It's stretching it out because the force of the spring is equal to the force of gravity when we're just going to equilibrium, which is what we're doing. We're changing equilibrium from here to here. So that means that my force of the spring is equal to the force of gravity, and the force of gravity is always mg. So that means that I'm going to plug in for Fs, mass, which is 0.2, times g, which is 9.8. Should be 0.196, but I want to make sure I'm not doing anything dumb. Good. So we get 1.96. And to get k by itself, we're going to divide both sides by 0.25. And the reason I'm dividing by 0.25 is these negatives will cancel. Negative and a negative cancel out to give you just a positive. So I'm just going to divide by regular old 0.25. When I do that, I get my value for K to be 7.84. And there is a unit for K. It's newtons per meter. It's actually very easy to figure out. You don't really need to memorize it. So what does the unit need to be for force? Newtons. What is the value for X? Meters. So it's just newtons divided by meters. That's where it comes from. All right. Any questions there? All right. Let's knock this out. We're almost done. Number 7. What's the equation for period of a spring? That we did in the spring lab. So, period of a spring is period S, and again, that's for, remind you, this is spring, not pendulum, is equal to 2 pi times the square root of, so just like the pendulum, it's the square root of directly proportional over inversely proportional, so it's the square root over directly proportional. Oh, wow, that is, oh my gosh, there we go. Directly proportional over inversely proportional. There you go. Period is equal to 2 pi squared m over k. Ts is the period of a spring. M is the mass on the spring. It's not the mass of the spring. It's the mass on the spring. And K is the spring constant. So what is the period of the spring in number 6 if it were allowed to oscillate? So if we let it bounce up and down, okay, here it is. If we allow it to bounce up and down, right, so go up and then come down and then go up and then come down. If we allow it to do something like that, what's the period? So we're solving for period. The mass was given in the problem. The mass on the spring was 0.2. So the mass here is 0.2. And the value for K we just found. The value for K we found was 9.84, or sorry, 7.84. So plug into the equation. Period is equal to 2 pi times the square root of m over k. So to solve this, I don't need to do any funky squaring things or square. All I got to do is do the numbers. So 0.2 divided by 7.84 gives me 0.0255. Square root that number. Period is equal to 2 pi times 0.160. Multiply that by 2. Multiply that by pi. We get the period equal to 1 second.